Welcome, and here I'm going to show you how to calculate the acceleration of something that rolls without slipping down an incline and also the force of friction that's acting on it. So we're going to do this using Newton's second law for rotation, which is angular acceleration equals net torque divided by rotational inertia. But the first thing I want to share with you is you have two options for how to do this. And those two options are dependent on what frame of reference you are in. So here's what I mean by that. If you're in the frame of reference of the rolling object itself, so let's just imagine for a second that this thing actually has some sort of a metal axle here that sticks out the front and sticks out the back. And let's say you're a little bug that's sitting on that axle. So as this thing rolls down the incline, you're gonna be moving with it. So in your frame of reference, as you watch this thing, it just looks like it's purely staying in place and rotating. So that's what we call pure rotation. And if you use Newton's second law of rotation from that frame of reference, then the object is rotating around its center of mass. And so you're going to add up the torques around the center of mass, and you're going to divide by the rotational inertia of the center of mass. Now, the other frame of reference is if you're in the Earth's frame of reference, in which case you're not moving with this object, you're watching it go down the incline. And it's both moving forward and it's rotating at the same time. And that's really what rolling is. And in that situation, it's actually the bottom of the rolling object, the spot that touches the incline itself, that is the center of the axis of rotation. So the axis of rotation is really down here when you're in the Earth's frame of reference. So in that case, you're going to be adding up the torques around this parallel axis, and you have to use the rotational inertia around the parallel axis as well. It turns out that this is the easiest way to get the acceleration of the object. So I'll show you how that works. So I always recommend drawing a free body diagram. And when you're doing torques, you don't want to just draw a dot. You want to draw the actual object itself that has the torques acting on it, because the location of where the forces are acting is really important for figuring out torque. So there's certainly a force of gravity acting on this object. I like to sometimes symbolize that as mg. Now, every single atom on this object experiences a force of gravity, so we would have billions, if not trillions, or more arrows of weight vectors. But that's what center of mass is all about. We always draw the weight vector coming from the center of mass because that's the average location of all of those weight vectors. All right, now there's a friction force. It doesn't roll unless there's friction. And so the friction force is acting right at that contact point. Also at the contact point, there's going to be a normal force, which of course is perpendicular to the surface. So that's it. Those are the three forces that are acting on this object. Now, like I said, we're going to use the point where it touches the incline to be our axis of rotation. So now we're going to have to add up the torques around that location right there. And so let's think about what they are. Well, first of all, I always like to just think about the forces and think about them in terms of torque is equal to radius times force times the sine of the angle between the radius and the force. So, all right, let's talk about friction. So in this equation, radius is always the distance between the axis of rotation and the location where the force is being applied. And with our axis of rotation down here, the distance between that axis of rotation and where the force of friction is being applied is 0. So the force of friction doesn't exert any torque when we have the axis of rotation down here. That's actually a good thing because we don't know the force of friction, and it'll cancel out that unknown from our equation. All right, same thing for normal force. The distance between the axis of rotation and the normal force is 0. And so normal force has 0 radius and 0 torque. So that means the only force that has any kind of a radius, so the distance between, I'm going to draw it maybe in green here, the distance between this axis of rotation and where the force of gravity is being applied, That distance is the same thing as the radius of this rolling object. And so the torque for the force of gravity is going to be R times the force of gravity, which is mg, times the sine of the angle between these two vectors. That's this angle right here. Now, it turns out that that angle is exactly the same as the ramp angle. I'm not going to prove that in this video, but it is. So I'm just going to do sine of theta here. Also, is this torque positive or negative? Well, if you use a traditional right-hand rule, you would see that your thumb points into the screen, which is a negative torque. But, it's always up to you to choose what direction is your positive direction. And since we know this thing is going to have an angular acceleration in the clockwise direction, that's which way it's going to roll. Let's just make the clockwise direction the positive direction so we don't have a negative sign to deal with. And you're totally okay to do that. Okay, so now we have to do the rotational inertia. But again, in this reference frame, it's not rolling around the center. It's actually pivoting around the bottom. And so if I look up, this was supposed to be a solid disk. If I look up the rotational inertia for a solid disk, it is 1/2 mr squared. But then using the parallel axis theorem, I have to add mh squared. H is always the distance between the center of mass, which is right here, and where this other axis is, which is right there. Well, in this situation, that's just equal to the radius of the object. So now let's see if we can simplify this to some degree. Definitely the masses cancel out. Definitely this radius will cancel out the squares down here. And so what we're going to end up with is g sine theta divided by, and now this is a half, and the coefficient here is really 1. So that's going to add up to 3/2 r on the bottom of this equation. Now, keep in mind, that's not our final answer. That's just what alpha is equal to. I was interested in what a is equal to. And here we're talking about the tangential acceleration of the outside of this object, because this object is going to be speeding up, and tangential acceleration and angular acceleration has to do with speeding up. So what's the relationship? Well, alpha, which is radians per second squared, is just equal to tangential acceleration, which is meters per second squared, divided by the radius. When you divide meters per second squared by meters, you get the meters canceling out, and you end up with radians per second squared. So let me make that substitution. A over r is equal to g sine theta over 3/2 r. And so this r cancels out that r, and we have a final answer of 2/3 g sine theta. Oops, sorry. My pen is giving me trouble down here in the corner of the screen. 2/3 g sine theta. And that's a little bit of an interesting result, because in the past, we've figured out the acceleration of something that, like a block that doesn't roll, but just slides down an incline with no friction whatsoever. And when a block slides down an incline with no friction whatsoever, its acceleration is g sine theta. So you'll notice this is some fraction of g sine theta. And if we had used a different rolling object, like a solid sphere or a hollow sphere, we would have simply gotten a different fraction of g sine theta. So you're always going to get a fraction of g sine theta here. Okay, so now how do we figure out the force of friction? And remember what happened here, that when we had our axis of rotation down where the object touches the surface, there was no radius for friction, so friction canceled out of our torque equation. So one option we have is to change where our axis of rotation is. That's exactly what we're going to do. And now we're going to calculate the torques around the center of mass. So let's take a look at what that looks like. So this is going to be adding up the torques around the center of mass. So down here, we're going to have the rotational inertia around the center of mass. Okay, let's see what that looks like. So now if our axis of rotation is at the center of mass, now it's the force of gravity that has no radius. The force of gravity, we always draw that acting at the center of mass. So there's no distance between the center of mass, which is our axis of rotation, and where the force of gravity is being applied. So the R for the force of gravity is 0. But out here now, one radius away from the axis of rotation, from the center of mass, we've got the force of friction and we've got the normal force. So it turns out, though, that the normal force doesn't exert any torque. Why is that? Well, let me draw that radius. So here's our, let me draw a different picture so it's not so sloppy. So here's our axis of rotation. This would be the radius, the distance between the axis of rotation and where the force is being applied. And then normal force looks like this. So what is the angle between those two arrows? Some people say 0 degrees. Technically, it's 180. They point in exactly the opposite direction. But whether it's 0 or 180, the sine of 0, the sine of 180 equals 0. So normal force doesn't exert any torque here because of the angle between normal force and the radius. How about friction force? Well, the angle between friction force and the radius is 90 degrees. So the friction force does exert a torque. So the radius for the friction force is just r, the radius of the rolling object itself. The force is the friction force, and the angle between the friction force and the radius is 90 degrees. Now, this would make it rotate clockwise, which for this problem, we're going to say clockwise is positive, so I'm just going to leave that without a negative sign there. All right, and then here I need the rotational inertia around the center of mass, which for a solid disk is 1/2 mr squared. Don't need to do anything with the parallel axis theorem there. And why don't I also do what I did last time, which is substitute alpha in place of alpha. I can put A over R, and that'll let me cancel out the radii. So this radius cancels out that square. This radius cancels out that R. And so what we're going to end up with is A is equal to, I'm going to move the 1/2 to the top here. A is equal to 2 times friction divided by the mass. And to get a final answer now, I'm going to substitute in what we got over here for the acceleration. So 2/3 g sine theta is equal to 2 friction divided by mass. Looks like the 2's are going to cancel out there. And so if I now just solve this for friction, friction is equal to 1/3 mg sine theta. So friction is some fraction of g sine theta. And actually, that's an interesting result as well. But in order to see why that's an interesting result, I want to show you one more option you have for analyzing this type of problem. In fact, let me just kind of write some notes here that might be helpful to you. So what I'm going to call this is options for, if I could actually hit the right keys here, options for analyzing a rolling problem. The one option is make the axis of rotation where the object touches the surface. You saw what happened when I did that. Here's another option. Make the axis of rotation where, at the center of mass, at the COM. All right. And so when you do the first option, of course, the equation you're going to use is alpha equals adding up the torques around the center of mass divided, oops, that should be the parallel axis. Adding up the torques around the parallel axis divided by the rotational inertia around the parallel axis. Here, you're going to use adding up the torques around the center of mass and the rotational inertia of the center of mass. But there is one more option, and we're going to use that option right now, and that is to simply use the linear version of Newton's second law. And by that, I simply mean acceleration equals add up the forces divided by the mass. Now, one thing about that equation is what acceleration are you getting? because for a rolling object, different parts of it actually do have different linear accelerations. It all has the same angular acceleration, but they have different linear accelerations. So it turns out whenever you use Newton's second law, you really are getting the acceleration of the center of mass. That's what you're always finding when you use Newton's second law. You're finding the acceleration of the center of mass. So let's do that now. And to do Newton's second law, we need to do a traditional free body diagram, one where all of the forces are just coming from a dot. So you do not need to do any kind of a torque or rotational free body diagram when you're just using the traditional Newton's second law. However, we do need to do things like tilt our axis and find components of forces. You don't have to tilt your axis with torque equations because the sine of the angle is automatically in the equation. Okay, so this is what our free body diagram would look like if we're just treating this as a linear forward motion, which it does have. It has linear forward motion. So in that case, the acceleration of the center of mass is equal to, and we're going to say this is the positive direction. So that's going to be mg sine theta minus friction divided by mass. Of course, this acceleration is the same as the acceleration we calculated up here, 2/3 g sine theta. So let me substitute that in. So 2/3 g sine theta. Actually, quite frankly, I didn't need to do that. What I really wanted to show you here is that this is what determines what the acceleration is going to be. It's going to be mg sine theta minus some friction. And again, thinking back to that situation where we had just a block and no friction whatsoever, where we got an acceleration of g sine theta. That's the maximum acceleration you can have down an incline. That's because if there's no friction, then the only force down the incline is mg sine theta. When you have a rolling object, it cannot roll unless there's friction. Otherwise, it's just going to slide down. And so this is why rolling objects have a smaller acceleration than something that's just sliding, because they're always going to have minus friction. And in this case, where did we calculate that friction? Somewhere we calculated it was, I thought we calculated it was, how did that disappear completely? Oh, there it is up there. We calculated that friction as 1/3 mg sine theta. So the net force is mg sine theta minus 1/3 mg sine theta, which is 2/3 mg sine theta. And that corresponds with this acceleration that we got here. Okay, so hopefully that helps you to understand the options that you have for analyzing an object that is rolling down an incline.